Welcome to this Supergen offshore renewable energy webinar. It is on co-locating wave and offshore wind, and there's going to be two presentations. The first one will be by myself, and it will be on work that we've done in WES on this topic. And then the second one will be by Abel Arredondo Galeana, who's at the University of Strathclyde. So without further ado, I will move on to my presentation. So it's on combining wave energy into wind projects, and this is based on a few different collaborations that WES has done with various partners. So the first one is the University of Edinburgh, the second one is OWC, and the third one is Blackfish. So what am I going to talk about? Why are Wave Energy Scotland interested in co-location of wave and with wind? The OWC study on techno-economic benefits of including wave in floating offshore wind projects, multi-wave absorber platform study, and finally the Blackfish wave energy cluster concept design. The intention of this presentation is more to signpost work that we've done, and you can find the reports on the various things on our website. So why do we want to do this? In Scotland, there's recently been launched a Crown Estates leasing round for wind farm sites, both fixed and floating. And these are moving into areas of the sea that were traditionally being considered for wave farms. And as you can see by the pictures on the right, the sea is very, very crowded with various uses. So it's likely there's going to have to be some sort of sharing between wind and wave. So there's cost benefits for both technologies of doing this. Potentially, we can share electrical cables, etc. Potentially, you can get better energy production by a farm area by using two sources. Wave energy can be available when you get lulls in the wind. And related to the last point, there can be a benefit for storage of having both things on site. Moving on to the OWC study. So Wave Energy Scotland asked OWC to do a technical economic study of combining wave into wind projects, and they looked at a lot of different levels of sharing of infrastructure, and they got some quite interesting results from doing this. The main one is the one that's highlighted. You get some level of cost benefit with even a modest level of sharing, and then you can get up to 12% of benefit by for a whole project by combining the two technologies. So moving on to the multi-wave absorber platform study. This study was motivated by thinking about how you get wave into wind projects. And there are a couple of factors in doing this well. The first is that most wave energy converters being developed are currently sub 500 kilowatts, and to meaningfully include these into a wind farm project, we really need to get the rating up. particularly as floating offshore wind turbines have ratings bigger than 15 megawatts. Another consideration is ease of deployment in the farm, and finally, there's trying to make the most of the wind supply chain. So one method of doing this that's been proposed by developers is to put absorbers onto the platforms that are being developed for floating wind. Potentially, these could be hybrid platforms, but for the moment, the developers of wind farm projects think that's too high risk. So that might be something for the future, but not for now, it would seem. So the viability of putting absorbers on platforms is dependent on hydrodynamic interactions between the absorbers, and also how the motion of the platform affects the absorbers. So WES have looked into this through our so-called MWAP study, which has looked at which has explored the performance of a notional multi-absorber system and comparable systems through the lens of physical and numerical modelling. This is work that we've done with University of Edinburgh, led by Flowwave. So the first part of this is the physical modelling. So a reconfigurable platform was designed and built by Flowwave, and the dimensions of the platform roughly correspond with semi-sub platforms that are being developed for floating wind, the likes of WindFloat or the TetraSub. And the platform allows a total of 9 absorbers to be mounted, and mounted in a way that minimizes the impact of destructive interference on the annual energy production by the platform. This is a key concern when modeling arrays, and that spacing is compatible with the dimensions of actual floating wind platforms. We've tested this platform with various moorings, including holding the platform fixed, and with 2 absorber arrangements, a 3 absorber 1 and a 9 absorber 1. The absorber itself is a submerged pressure differential WEC. It's loosely based on wave swing, which is a kind of point absorber that has its restoring force supplied by a combined air and hydrostatic spring. That's difficult to simulate at model scale. So Flowwave developed this PTO. Flowwave developed this PTO assembly that combines a mechanical spring and a PTO spring that's mounted above the absorber, and this allows us to simulate these things. We can only do passive PTO damping control with the test platform, but that's adjustable through motor control. In the numerical modeling, we did frequency domain modeling of the MWAP configurations that we're looking at in the tank test, and also some alternative systems that allow us to do some comparison with alternative systems. Again, we can look at different moorings with a numerical model. We were intending to do calibration and validation of the tank tested systems, but that's not been possible for some reasons that I'll explain later in the presentation. So in both the tank tests and the numerical modelling, we looked at our wave resource. We performed performance testing and modelling for a wave resource that's at the Magnora Talisk wind farm, which is one of the lease sites that was awarded to Magnora, one of the Scotland lease sites. Sorry. Um, for this, I got wave data from the resource code database, and the resource at the site, which is this one here, is about 60 kilowatts per meter. We've only looked at long crested seas at this stage, but it would be feasible to look at short crested seas in the future. In the numerical modeling, we've looked at 5 different control and constraint handling approaches. This is quite a complicated slide, so I'll break this down into different parts. So the first thing to say is all the control strategies we've considered are diagonal, and that basically means the same control parameters are applied to all the absorbers. Secondly, in the control and constraint cases that are highlighted, we've looked at optimal diagonal control for the unconstrained systems. On top of that, we've looked at constraints using an approach that was developed by McCabe, and that basically is a post-processing approach for looking at the constraints that are indicated on the slide. And finally, we've looked at control that's optimized for a single absorber. And with that, we've been able to include constraint handling in the actual optimization process using a constraint handling approach developed by De Backer. So you can find a lot more details about these control and constraint handling options in the paper that we presented at UTech, that's available on the WES website. The two constraint handling approaches both have pros and cons, and if there's time, I can talk some more about that in the questions and answers. So from the physical modeling, we got a couple of useful learnings and also encountered some issues. The useful stuff, we managed to do some validation with numerical models for the platform. That included Orcaflex platform simulations, and we also managed to do some validation of the absorber excitation forces. We also got a lot of useful insight on things that are not currently represented in the numerical model, which is a frequency domain model. So we found that the hydrodynamic and hydrostatic forces on the underside of the lid of the absorber affected what the absorbers were doing. That's not currently represented. We also found that the absorber operation can destabilize the platform, which is a nonlinear effect. We also found that platform motions can inhibit the absorber operation. For example, if an absorber comes out of the water. Moving on to the issues, we found during the tests that the absorbers had visibly different personalities. These were visibly down to differences in friction and stiction in the drivetrains of the absorbers rather than hydrodynamic phenomena. This is as the slide says, this is an unfortunate challenge of testing such a complicated system at small scale. Moving on to the results of our numerical modelling. We found in our comparisons between the configurations that the Q factors only diverge moderately from one for all cases. We got almost identical Q factors for the small array configuration, which is this bottom one, and our platform option, which is this one. How you handle constraints had quite a big influence on what results we got, and we saw a lot of constructive and destructive interference for individual C states. The results that are presented are for an annual Q factor, which is what's defined here. So it's the annual energy production of each absorber summed over the number of absorbers times the AP of the solo absorber. Not covered by this table, but in our UTEC paper, we saw that the annual Q factor is relatively insensitive to the direction of the incident C states, and we saw across C states quite a lot of variation in the power capture between absorbers. So moving on to the Blackfish wave energy cluster concept design study. We commissioned Blackfish to identify and develop wet clustering concepts which can create multi-megawatt platforms with low LCOE, enable offshore maintenance, easy offshore maintenance, lower installation costs, be compatible with offshore wind, be deployed in deeper waters. This was just done at the concept level. We didn't go into the physics of the systems or the actual practical engineering design. You can see a report of this stuff on the WES website. So to conclusions. The main conclusion from the OWC studies is that you get some economic benefit of integrating wave into wave projects. Wave into wind projects. Those benefits increase as you increase the amount of integration. And then on the multi-wave absorber side, we saw that the annual AEP, the AP of our model configurations is only moderately impacted by hydrodynamic interactions. That's likely to change if you have absorbers closer together or a different platform. So that would need to be reconsidered for other platforms and absorber systems. Our physical modeling shed a lot of light on the physics of the systems not addressed by our numerical models. And overall, based on our modeling to date, WES haven't ruled out this kind of multi-wave absorber platform system, but you're probably looking for reductions in capital costs. Well, costs overall, or boosts in AEP to make it an economically attractive thing compared with installing the absorbers in arrays. Finally, the Blackfish wave energy cluster concept design study. That study indicates that there's possible routes to viable platforms for MWAP systems. that are not wind platforms. And finally, some ongoing work and potential future work. There's a PhD student that's continuing to work on the MWAP stuff. He's currently looking at using the kit that was developed for the MWAP study to get a better grip of on the validity and limitations of the numerical modelling. He's also looking at some other configurations and changing the absorber size to see how that affects the performance. Possible future work would be to look at more realistic and advanced control. Think more about the nonlinear effects in the MWAP numerical models. There's a time domain model developed by the University of Edinburgh for that purpose. And on the Blackfish concept study side, explore the engineering and wave energy of the concept developed further. And then moving on to a real system is developed more optimized co-design systems. And that's me. So I'll hand over to Abel to do his presentation now.
Thanks, Niall. Let me share my screen. Hopefully that's showing. Okay, well, my name is Abel Arredondo Galeana. I work at the University of Strathclyde. I'm a research fellow, and I'm also part of the early career editorial board member of the Journal of Fluids and Structures, in which you're kindly invited to consider submissions in case you have some relevant publication coming up. The title of the presentation that I'm gonna give today is, and sorry for the long title, it's Preliminary Observations on Synergetic Effects in a Nature-Inspired Wave Wind Farm towards a reliable baseload for offshore hydrogen production. And the results and slides that I'm presenting to you are derived from the work we're doing for two major EPSRC programs in the UK. One of them is Ocean Refuel, in which we are investigating the possibility of offshore hydrogen production as a green energy vector alternative for current methods, and part of the Supergen program as well, which is hosting us today with Wave Energy Scotland in this webinar. So the topics that I'll try to cover is a little bit of introduction between the difference between hybridization and collocation, and between wave and wind. Why is it that we're interested in this from our point of view? What are some key design considerations that we have learned along the way? And some results in terms of metocean conditions, hydrodynamics, power performance, and hydrogen production alongside some final reflections. So in terms of combinability of wave and wind, well, we essentially have looked at two possibilities. One is a fully hybrid design of a platform in which you design a platform that is meant to produce capture wave energy and wind power in one single, let's say, floating platform. And alternatively, you have the option of collocation, in which you don't have to design something radically new, and you can use already operational wave energy converters alongside wind turbines, in this case, floating wind turbines, and you can see how they interact between each other. And this is the approach we're going to be looking at in this presentation today, the collocation approach. Why do we want to collocate? Well, as part of the one of the insights that have come from the Ocean Refuel project is that hydrogen electrolyzers They don't like the intermittency of wind energy, and that's because they're designed to operate in steady state operation. So they require a minimum power and base load to keep a continuous operation, and therefore have a less detrimental fatigue life, let's say, in terms of operation. And so these periods of absent power of wind energy are the ones that we're trying to see if we can patch with the wave energy component, and therefore prolong the life of the electrolyzer when it's installed offshore. As another side of this coin that we're looking at is in terms of cable utilization. And so because the cable utilization is an important cost metric, if we can improve the utilization of the cable through power density availability or power downtime reduction through the combination of wave and wind, we directly impact the economics of a floating wind farm and a wave array as well. So these are our two main drivers at the moment. Some key design considerations that we've learned along the way are, well, we need to, for these co-located wind farms, we need to be looking at metocean conditions, the environmental loading with the hydrodynamic aspects of the wave and semi-sub interactions. Cost constraints, the part that I was talking about when you combine this wave and wind energy sources, you can effectively reduce some costs, power performance, and the layout of the wave wind farm alongside environmental aspects as well. So I'm gonna talk about a few of them, not all of them, but in terms of metocean conditions, well, it's very important to characterize the location where we're planning to deploy these combined wave wind farms, and essentially you have very different characteristics if you go to the Atlantic coast of Europe, where you have swell-dominated waves, or where if you go to the North Sea, where you have a higher wave and wind correlation, and well, the local wave is directly correlated to the local wind, and this will affect the performance of your wave wind farm and in terms of what objective you're trying to fulfill. In the case of the case where we want to patch these periods of absent power of wind, we have found that locations that have swell type of waves are most preferred because because the local wind is not related to the local wave. The local so the correlation index is quite low. So that's an important aspect that we're looking at. And the second metocean aspect is the seasonal variability of wave power. And we have seen in our analysis that you do have this bathtub shape in a year where you have more wave energy density during the winter months and dropping towards the summer months. And well, in these swell-dominated regions, the power density is quite important and full of energy. In terms of hydrodynamics, and this is where the nature-inspired concept came about, we tried different configurations, and we accidentally remembered some previous studies where people have been looking at native-inspired swimming formations. And in this case, we're proposing a delta configuration for a combined array of buoys type of WEX in front of a semi-sub floating turbine. And the reason for this is we are trying to enhance the shadowing effect or make use of the shadowing effect behind the WEC and directly impacting the pontoon of the semi-subs in such a way that you have a reduced wave height hitting the pontoon downstream in the wind turbine. And for this, we're using potential flow theory. At the moment, it's a work in progress. and we're modeling the wave as a simple floating body and only with a single degree of freedom in the in heave and in the radiated with radiation in heave only. And what we've initially found, interestingly, is that with this configuration, we are able to demonstrate that pitch motion is reduced downstream in the semisub, and this can have an effect, importantly, in the power production profile of the turbine. And what I'm showing here is a simulation that we've done um, on a single semisub with different wave heights upstream of the platform to demonstrate what is the potential effect of shielding the semisub with wax in order to reduce the wave height and therefore change the delta in the power output of the turbine. We believe that this has also a potential benefit in hydrogen performance, and we're going to try to quantify that as well. Importantly, as part of the Ocean Refuel project, we've been looking at converting the power output of offshore renewables into hydrogen production metrics. So we're in this case, what you see on the left-hand side is the power curve of a 7 megawatt turbine with a timely resolution and specified there at the bottom. And you can see that there are periods of time where the wind turbine is shut down because the wind speed is below the cut-in threshold, or vice versa, is above the cut-out wind speed. So in these periods of time, for example, if you look at this period between 16 to the 18 hours here, your hydrogen production, and this plot here shows your cumulative hydrogen production in a station offshore where you're feeding directly the turbine power to produce hydrogen. And you can see that in these periods of time where you don't have wind power, your hydrogen production flattens out, and well, that's you're essentially losing money. So what we're trying to do, for people interested in this model, you can access the open source model for the electrolyzer in this GitHub repository as part of the Ocean Refuel project. And now what we've done is we've evaluated now the power production output of a combined wind and wave farm on the coast of Portugal with swell-dominated seas. And in this case, we consider a 5 megawatt floating wind turbine combined with 5 WECs of buoy type rated to 400 kilowatts. For this particular exercise, we're assuming a WEC of the C4 WEC from Core Power, and the power matrix that it's open access in the reference there at the bottom of the screen. And well, what you see in the top image is the power time series of wind power in black for a period of 2 months in January and February, so winter months in 2024. And overlap on that, we're producing the power output of the WECs, which are 5 WECs rated at 400 kilowatts. So at their maximum capacity, they're producing 2 megawatts. And you have there, let's say, a disparity of almost, you have the double power capability production in wind power compared to the WEC capacity. And in blue, you see the combined production power of wind and wave. And interestingly, I mentioned at the beginning that we were looking at regions where wind power drops below a certain threshold that is not sufficient for the electrolyzer to keep running. But wave power can come into action in these regions and provide that power surplus to keep the electrolyzer running. But you also see there are regions where you actually have both of the resources available, where if you look at this region here, you have wave and wind, and then you have more power availability in this. in this plot. So how does that translate to hydrogen production? So in this plot at the bottom, I'm plotting the time in hours for these 2 months in hours. So it's about 1,400 hours compared to total hydrogen production in kilograms. And in black, you see the production that you would have if you only had the wind power connected to the electrolyzer stack, as opposed to what happens when you have wave and wind. So the blue curve, which is a combined power connected to your electrolyzer stack. And well, initially, the aim was simply just to reduce these flat regions of no hydrogen production and see if we could just give them a bit of slope. But what we have found is that actually the effect is substantially more important, in the sense that actually the full slope of the curve is enhanced, and at the end of the 2 months, you're looking at an increased hydrogen production capacity of about double of what you would have only if you had uh, wind energy. So and this is a very promising finding, we believe, and it hints, or it tells us clearly that combining wave and wind power has clear benefits in terms of many aspects. In this case, hydrogen production. So, and some final reflections about the work we've been doing. Well, wave and wind collocation. We've been looking at wave and wind collocation in order to produce a minimum power threshold, and also we're thinking about optimization of export cables. Specifically, this talk we focus on that or supplying that minimum power threshold for the electrolyzer. We've designing a nature-inspired approach of a wave wind farm with a delta configuration to try to maximize the shadowing effect of the WEC in front of the semi-sub, and will reduce power oscillations in the wind power output that can have also a detrimental effect in electrolyzer performance. Site methods and conditions are key in designing the farm layout and in satisfying your design objectives. And so in this case, we have found that swell-dominated regions are important to satisfy this minimum power threshold condition. Initial results in our hydrodynamic modeling indicate that pitch motion suppression is achieved by a reduction of the wave height hitting the semi-sub, the wind turbine. And we have observed an important increase in hydrogen production that can reach up to 50% in 2 months, 2 winter months in a swell-dominated region, by combining wave and wind power. Obviously, this is a few caveats here. Well, this is dependent of the WEC device that you're studying, of the location that you're looking at, and also hydrodynamic interactions of the array. And that's something that is future work as well. So that's my talk, and we're happy to go through any questions from the audience.
Thanks, Abel. So I guess we can take questions for both talks together. We've had a few questions in the chat, which I guess we can start with. So the first one was from Stephen Redford, and he asked, have any of the wind farm OEMs given thoughts on how improved dampening for floating wind projects could be obtained from wind wake effects, is how I read that. I'm not aware that that's been done at this point in time, but it is an interesting conversation that we could have with the wind developers. I don't know if you have any thoughts on that, Abel.
Um, no, I think it's important to start getting wind turbine developers into the conversation, because they need to be made aware that this is not only beneficial for wave energy developers, but also for them. So I think we're in process to try to engage a little bit more with them, and yeah, that's my take.
Thank you. So there's another question in the chat that was targeted at me. Tony asks if our uh, he asks about loads due to the wind turbine. The focus of our modelling was really to understand how absorbers being close together uh, in, affects the performance of the absorbers, and also how the motion of how motions of the platform affects the performance. Um, so yeah, feasibly we could put the inertia and we could put the mass and the inertia into our models, into our numerical models, um, in order to look at how the wind turbine affects the performance. But we haven't done that at this stage. That's something that we could consider in future modeling. So that was the two questions in the chat. If anyone,
I think there's another comment from Jeremy.
oh right, okay, I haven't seen that yet.
Ignore. So I think this one is for me. I'll
Go,
take.
yeah.
I think it says Jeremy Simon's great results on cumulative H2 production seems relevant to normalize the mass production rate to mean power and to consider the peak to mean to capture the utilization of electrolyzer and other equipment. As you mentioned, the co-location can gain utilization of cables. But thanks, Jeremy. Yes, so I'll take on board your comments, and then we'll do some normalization on the cumulative H2. And yeah, so there's two sides of the coin that we're looking at, hydrogen production and see also if we can come up with metrics for cable utilization. Yes.
I think there's another one targeted at you, Abel, below that.
Is it Judith or John?
Yeah, John.
John, okay. Um, right. Thanks, John. Yeah, so regarding the shielding, well, we're at the moment we're just modeling a passive buoy. So we plan to include additional considerations in terms of PTO damping and some sort of mooring stiffness. But we expect that the shielding effect is significant because but we're already getting some interesting results without any control. In terms of the power production, yeah, we were also very pleased, and we haven't done OpEx calculations yet, but it's there's room to keep going. Yeah. I think there's another one from Judith, Niall.
Okay, the constraints. So we looked at the constraints with two approaches. The McCabe one, and in the McCabe approach, we just looked at constraints on the stroke and the constraints on the on the instantaneous power. And then with the debacker approach, we looked at constraints on stroke, velocity, and PTO force. From memory, with the debacker approach, the force and the stroke were the ones that had the most impact. One thing I would say about the constraint handling is we have a bit of skepticism about the debacker approach because it doesn't model how the constraints being triggered impacts on radiation of waves between absorbers. So I think that's what I can remember at the moment. I can look into that in more detail if you want. If you can drop me an email about that, and I can tell you some more about it. Yeah. If anyone would like to come off mute and ask a question, you could put your hand up. Or we'll continue to take questions from the chat. I've got a question for Abel in the meantime.
Okay.
Is it diffraction by the wave absorbers that's causing the reduction in the motions of the platform, or some other effect?
Yes, you did ask me this before. So I think it will be because we have this without control at the moment. It could be certainly diffraction, but I think the moment we start implementing the control, it might become radiation, the dominant factor. So it's something that we still need to investigate with more detail. Yeah.
Okay, we've had a comment from Remy about engaging with project developers. Yeah, this is a very good point, and it's something that Wave Energy Scotland will definitely look into. Thanks for your comment, Remy. Okay, we'll stop there. Thanks for your attendance of this webinar.
Yeah, thanks very much, Nick.